This is our introduction to our acid and base unit, the last unit we'll be studying this year. Here are some examples of some acid-base chemistry. Now, when we look at the upper left, here we see what happens when an orange and chloral sulfonic acid, come into contact. Not turning out so well with the orange, right? Down below, one of the cool things that you can do with sulfuric acid is you can add it to a sample of sugar. And the reaction is pretty exothermic, releasing heat as the sugar has all of the water pulled out of it. Over here on the bottom right, you see gold. And when you mix in, the first mix was with hydrochloric acid, nothing much happens. Then when you mix in nitric acid, which also has some additional oxidizing properties that hydrochloric acid doesn't, you get a pretty interesting reaction where the gold starts to actually ionize, right? The solid gold turns into gold ions. And one of the reasons why gold is so treasured, right, is because, it takes a lot to actually degrade solid gold, right? Concentrated sulfuric acid is not enough to degrade the gold. And that's one of the reasons why it is so valuable, right? You need this mixture of nitric acid and sulfuric acid in order to get the gold to start to, ionize, which means that the solid gold itself is, dissolving into the aqueous solution. And then on the upper right, we can see the danger of bases because, we talk a lot about strong acids like hydrochloric acid on the right here with this Coke can, but a strong base like sodium hydroxide that you're familiar with, right, can actually also do some damage. I mean, look at what it does to this, can of Coca-Cola here on the upper left. Now, we've used both of these before in the lab, right? Sodium hydroxide in particular when we were making soap, and hydrochloric acid. Now, the concentrations we were using weren't enough to do this to Coke cans right away. Now, that is another aspect of this unit we're going to talk about. How do scientists quantify concentration so that it's a mathematical and very sort of exact description of the acid? When you think about acids, it's not just the type of acid, but it's also their concentration. And that's on the bottom right. This 12M means 12 molar. And what we'll find out later in this unit, it sounds like moles, correct? Here's the nitric acid, 15 molar. So what we're going to be looking at is not just the acids themselves, but what does this molar concentration mean? Going on to the next slide. Things about acids, right? They taste sour. That's why when you, bite into a lemon, you get that sour taste on the back, right, of your tongue, and it's like, ooh, around the sides of your tongue, and you can definitely feel that, right? Vinegar owes its taste to acetic acid. So there are acids that we consume, right? Citric acid, acetic acid. These are what's known as weak acids, and we'll talk about what that means in a little bit. They react with metals to produce hydrogen gas. So when you saw in that Coke can, when it reacted against hydrochloric acid, there was some gas bubbling out of that solution, and it doesn't just take the solid metal and convert it to an aqueous ion of the metal, which floats around. It also often releases hydrogen gas, which can add to the danger because, as we know, hydrogen gas is explosive when in contact with oxygen gas and a spark. And when the heat is released from this reaction, that can cause it to blow. Now, another reaction with acids are with carbonates and bicarbonates. Sodium bicarbonate is also known as baking soda. And we're going to look at how acids and baking soda produce carbon dioxide gas, which is why your cookies rise, your banana bread rises. It's the bubbling of the carbon dioxide gas. Carbonates also react with acids to produce carbon dioxide gas. When we talk about the degradation of coral reefs, the acids that are in water can and do degrade the carbonates that coral reefs that are made of. Carbonates are what make up the seashells. For example, when you think about, oysters or clams, their shells are made of calcium carbonate, which is pretty water insoluble unless it's exposed to acid. Another property of acids you may remember from previous middle school experiments is they turn blue litmus paper red, and they have a pH less than 7. Low pH is acidic. Bases, on the other hand, have a bitter taste, which is slightly different than a sour taste. They feel slippery, and many soaps contain bases, as we've learned, right? Bases are used in the chemistry of soap making, saponification, converting, right, the fats and the oils that you initially start with to molecules that have both polar and nonpolar ends. They turn red litmus paper blue, and bases have a pH greater than 7. Here are some examples of acids: hydrochloric acid, sulfuric acid. Notice that if sulfuric acid looks like this, when you have an acid that ends in ic, like sulfuric acid, one less oxygen is sulfurous acid. Another interesting fact is the ic form is always more dangerous than the us form. This is a stronger acid than this. This is nitric acid, one less oxygen, nitrous acid. Here again, hydrofluoric acid, we're starting with a hydro. One of the patterns that you'll also notice here is that when you just have one nonmetal or one type of nonmetal, that's when we start with hydro. Hydrofluoric acid, hydrochloric acid. You're probably familiar with hydrochloric acid from learning in biology, right? This is the acid that our stomachs produce to actually degrade the food that we eat. It's part of the digestion process. Notice that sulfuric acid is not just an S but O's. When you have nonmetals complexed with oxygens, right, this is the sulfate ion. If you look on the back of your periodic tables when we learned about the polyatomic anions, sulfate, whenever you have an 8 ion, it turns into the ic form of the acid when hydrogens are added. Notice that this was -2, and each +1 hydrogen balances this to 0. -1 for chloride with a +1 hydrogen, HCl is balanced to 0. Hydrofluoric acid, you're probably familiar with in art class if you've ever etched glass. That's what's used for that. Acetic acid is what's the active ingredient in vinegar. And this is the old way of writing it, and it's persisted. It tells you a little bit about the structure. So it's C with 3 single bonds to hydrogens, single bonded to this carbon. And then this carbon is actually double bonded to an O up here. And then this O is bonded to the carbon also, and then the H is bonded to the O. Carbonic acid, notice the carbonate ion makes carbonic acid. Phosphoric acid and perchloric acid. Phosphoric acid is one of the acids found in Coca-Cola, and carbonic acid is also found in all sodas. It's the acid that forms when carbon dioxide is bubbled into water. Carbonic acid is present in any carbonated drink that you enjoy. It's responsible too for that a little bit of burn that carbonated water has as opposed to non-carbonated water. So if you haven't noticed the pattern yet, I'm going to challenge you. What is similar about almost every single one of these molecules? What element do they start with? And also, what type of molecule are these? Are these ionic or covalent? Hopefully you noticed that trying to identify an acid isn't really that hard usually, because if the molecule is covalent, all of these are, right? They all contain just nonmetals. There's a chance that it's an acid. And 2, most of the time when an acid is written, the hydrogen, right, is written first. Notice that in all of these examples, we see hydrogen followed by other nonmetals. You know, the more modern way of writing acetic acid, does involve this, but I include it this way because this is the more common way. You're just going to see it. So there are some acids that don't have the hydrogen placed first, but almost all of them do. So in order for you to identify an acid, covalent, it's made of all nonmetals, and they start with hydrogen. So what exactly do acids do that make them reactive chemically? Well, notice that HCl and water can undergo a chemical reaction. When you look at what's formed, H3O plus and Cl minus, I think you can sort of glean what the chemistry was. An element transferred from here to a water. And it's pretty obvious that that element was this hydrogen. So when an acid transfers one of its hydrogens to water, it produces H3O plus, known as the hydronium ion. Now sometimes, so this represents the physical reality. And when we encounter acids and we use them in the lab, they're almost always aqueous solutions. So what acids do when you add them to water is this. They form the hydronium ion. So if you were to stick your finger in a beaker of acid, this hydronium ion is what's going to start to degrade your skin. If you're eating lunch and you pull apart your orange and some of the orange juice squirts across the table and lands in your friend's eye and they scream, that is what's burning in their eye, is the hydronium ion. Now, excuse me. Shorthand, sometimes chemists will leave out the water in this reaction. And what they will show is simply what's happening to the acid itself. However, it is understood that this physical reality is what's really happening. In other words, the proton, as it's sometimes called, right? Because protons, the subatomic particle, protons really are what an H plus is. Because if you think about it, most hydrogens actually have 0 neutrons. So with a proton and no electrons, H plus ions are simply just referred to as protons. The physical reality, however, right, is that this water is turned into a hydronium. So really, without the water shown, it looks like this, but chemists know that this, in reality in water, is really the hydronium ion. So how would you do this on your own? Sulfuric acid, H2SO4. What would you do to show what happens when this is added to water? The difference between hydrochloric acid and sulfuric acid is 2 protons. And it is possible for both of those protons to come off. Water, however, most of the time only one comes off. If you showed it like this, you are correct. Now, how do you know what to do? Let's review. If this chloride and this proton are together in a bond and they separate, one of the things about acidic reactions is the proton itself leaves without the shared electrons in this covalent bond. Chloride keeps both electrons that are shared in this bond. That's why the proton is that's why this is positive. The hydrogen becomes positive 1 because it leaves its electron behind with chlorine. And when chlorine gains that electron, extra electron that was in this bond, that was originally donated by the hydrogen, it becomes chloride. Also, because chlorine is in group 17 of the periodic table, it can gain 1 electron to achieve its octet, and hydrogen loses 1. Looking at the example below, if there's 2 hydrogens, each of them can lose 1 electron, which means that the SO4 becomes sulfate with an overall charge of -2, taking both of those electrons. So when you lose 2 protons, the resulting anion is 2 negative. Now there are strong acids and there are weak acids. And the difference between this is how well they dissociate and fall apart. A strong acid, like hydrochloric acid, when you put it in water, and then sometimes we just show the water above, meaning it's there, but we're just going to look at just what's really happening outside of the water, right? The protons and the chloride ions. Which means if you put 100 molecules of this in water, the straight arrow across, and understanding that this is a strong acid, you get about 100% of these HCl's falling apart. And you really have none of these left over in this form. They all transition to H plus and Cl minus. So for every mole of hydrogen chloride or hydrochloric acid you put in water, they fall apart and you get 1 mole of protons and 1 mole of chloride ions. Weak acids are called weak because when you put them in water, they do not dissociate completely. This is what's known as acetic acid. Acetic acid only dissociates, and weak acids in general, only about 5% dissociate. Excuse me, we'll go back to that in a sec. Only about 5% dissociate, which means that if you put 100 molecules of acetic acid in water, you have about 95% remain in this form on the left. That's known as the protonated form because it has the proton. And this is the deprotonated form, D meaning without. So you only get about 5% ionizing into this form on the right. And if H plus is truly the acid part of acid, it's what really does the chemistry when interacting with other molecules. Here you get 100% dissociation with hydrochloric acid, and here you only get about 5%. So the next time you go to, a store, whenever that may be, and your parents drag you to some fancy store that has lots of fancy vinegars in it, or just go into your own cabinet. Take a look at the back of the vinegar bottle, like the balsamic vinegar bottle, and they may tell you the percentage, and it says usually around 5 or 6%. And that's about the percentage of protons in there, which is why we can drink it and not burn our throats entirely. What are some of the common strong acids? Hydrochloric acid, nitric acid, perchloric acid is pretty strong, and beneath it, sulfuric acid, though like I said before, generally only one of the protons is strong. And when you only take 1 proton off, look what's left behind. Instead of sulfate with 2 minus, you have the hydrogen sulfate ion with -1. And as I mentioned before, strong acids dissociate completely, and weak acids only dissociate partially. And that's what this double arrow generally is there to indicate to you. The double arrow tells us that we have only partial dissociation. To take a quick look at this visually, if you have just water and you add a strong acid to it, okay? Ooh, and we can measure the pH also. And you add a strong acid to the water, notice that if the acid is in the form of HA, meaning here's your proton, and A is just a generic, it doesn't represent any particular sort of non-metal, it's just a sort of generic non-metal, then the A minus, that results when the proton is lost from the acid, right, and the hydronium ion that is formed. Notice that how many of these HAs do you actually see left in the water when it is a strong acid? Almost none, or actually I don't see any here. And what's our pH? Our pH meter tells us it's about 2. Now what about when we have a weak acid in water like acetic acid found in vinegar? Notice that the HA, there's plenty of these left over, meaning almost all of it stays in this original form. Notice that the hydronium ions are much smaller in concentration, right? As compared to the strong acid, the weak acid only has a small amount of hydronium ions created. So, just to summarize, only about 5% of weak acids dissociate. Only about 5% are converted into the hydronium ions. And what you'll notice right here, water can act as both a weak acid and a weak base, as we will find out. What are bases? Well, if an acid, so the simplest definitions of acids and bases are attributed to Arrhenius, the chemist who originally classified and studied them. If an Arrhenius acid produces protons in water, an Arrhenius base produces OH negative or hydroxide ions in water. Now here, sodium hydroxide is the most famous base of all, also known as lye. It's the active ingredient in Drano because bases, unlike acids, most bases at the concentrations that we use won't dissolve the metals that your pipes are made of. So when we add sodium hydroxide or sometimes potassium hydroxide in Drano into our sinks, it reacts only with the hair and the gunk to dissolve that, and it doesn't dissolve the metals. Magnesium hydroxide is another example. Now, I hope that when you actually really think about this, you notice NaOH, MgOH, sodium, magnesium, these are metals. Hydroxide, non-metal, hydroxide. So, how do you identify bases just by looking at their chemical formulas? Well, if acids were covalents that started with hydrogen, bases are ionic compounds that start with a metal and they end in OH, hydroxide. Metal, hydroxide. When you put them in water, just like acids, there is a dissociation that happens. And instead of releasing protons, you release hydroxide ions. There are strong bases, such as metal hydroxides that are made of group 1 and 2 metals. Sodium and potassium are both group 1. Barium is group 2. And notice that with +1 metals, because hydroxide ions, -1 charge, if you take a group 2 metal, you must balance the +2 with 2 of the hydroxides. But when you release them into water, you can produce 2 moles of hydroxide for every 1 mole of barium hydroxide. Acids can also be strong or weak. And one thing we'll notice and one thing we'll learn is that water is said to be an amphoteric substance. It is both a weak acid and a weak base. So the reacting of water with different substances can produce both hydronium ions and hydroxide ions. Well, that's the introductory video for now. Please go to the CK1 assignment where you'll test a little bit of your knowledge. Now, of course, you can use this PowerPoint to help you. I'm also putting a copy of this in the actual assignment itself. So you can refer back to this either if you wanted to go through it on your own or while you're working yourself through the acid-base quiz number 1.